Hello everyone, and welcome to week 5 of Abarso's 10th grade math Google Classroom. This week we will be reviewing how to graph quadratic and cubic functions. These skills are directly related to the competency of analyzing functions using various representations and will be assessed on the placement test you take upon returning to Abarso. As you follow along, take notes on the examples and definitions that are provided. These will be useful guides and can be used on the short quiz associated with this lesson. If you don't have them with you already, pause the video and grab your pen and notebook before we get started. Let's get started with the do now. I want you to graph the function f of x equals 4x plus 3 using an xy coordinate table. Pause the video now and give it a try. Right. A few things should have stood out to you. One, you should have realized that this function is a linear function expressed in the slope-intercept form. Replace f of x with y, and this point should be obvious to you. And as its name implies, a linear function will graph as a straight line. In order to get a picture of the direction of the function and some of its characteristics, I chose to plot some positive and negative values of x and solved for their corresponding y values. From this, I could tell that the slope of the line was positive and quite steep. The general technique for graphing quadratics is the same as graphing for linear equations. However, since quadratics graph as parabolas, rather than the straight lines generated by linear equations, there are some additional considerations we must include in our graphing procedures. The most basic quadratic function is f of x equals x squared. When we graph the function in our do now, if you were able to tell right away that it was a linear function, we technically only needed 2 points to graph our line. However, as I suggested, we plotted 3 or more points just to be on the safe side. 3 points will not be sufficient for plotting a useful graph of a quadratic. For example, suppose we compute these 3 points for our function f of x equals x squared. This graph would be wrong for several reasons. First, the individual points were connected with straight line segments. Secondly, after passing through the origin, the function takes on a linear appearance. To get a more accurate idea of how the function looks and behaves, it is wise to plot more points, both positive and negative. Plotting all these additional points, we see new characteristics emerge. Even if you'd forgotten that quadratics graph as curved parabolas, by graphing these points, you will begin to see the telltale U-shape take form. Connecting the points with a smooth, curving line passing neatly through the plotted points, we get our desired parabola, which accurately depicts the behavior of our quadratic function. For more complex quadratics, we can tell a lot about the eventual form of the quadratic by evaluating characteristics of the original function. You will remember that the general form of a quadratic is y equals ax squared plus bx plus c. For graphing, the leading coefficient a indicates how wide or how narrow the parabola will be. For the absolute value of a greater than 1, such as a equals 5 or a equals negative 6, the parabola will be narrow because it grows more quickly, 5 times as fast or 6 times as fast respectively in the case of our sample values of a. When the absolute value of a is less than 1, such as a equals 1/2 or a equals negative 1/8, the parabola will be wide because it grows more slowly, 1/2 as fast or 1/8 as fast respectively in the examples. If a is negative, the rules related to wideness and narrowness hold true, as we are considering the magnitude of the coefficient. However, the sign of the coefficient does affect the direction of the curve. Negative a values will be upside down U's, while positive a values assume the typical U shape. You can see these trends when you look at how the curve y equals ax squared moves as a changes. As you can see, the leading coefficient goes from very negative to slightly negative, and then from slightly positive to very positive. The parabola goes from narrow upside down to wide upside down, and then to wide right side up to narrow right side up. To remember these shapes and characteristics, you can think of your parabola in relationship to your lips and emotions. If you're feeling negative, you might frown, which takes the upside down U shape. If you're feeling positive, you might smile, which takes the typical U shape. This can be useful information. If, for instance, you have an equation where a is negative, but you're somehow coming up with a plot of points that make it look like the quadratic is right side up, then you will know that you need to go back and check your work because something is wrong. Moving on, let's consider the behavior of other functions. When we're graphing polynomials, it can help to already have an idea of what the basic polynomial shapes look like. One of the aspects that we should look out for is what is called end behavior, and it's fairly straightforward to observe. Let's look at some examples to find similarities and differences. First, let's look at some polynomials of even degree, specifically quadratics in the first row of pictures and polynomials with a degree of 4 in the second row with positive and negative leading coefficients. In all four of the graphs, for the period over which the graphs were drawn, the ends entered and exited in the same direction. When the graphs were of functions with positive leading coefficients, the ends entered and exited from the top of the coordinate plane, just like every positive quadratic we've ever graphed. When the graphs were of functions with negative leading coefficients, the curve entered and exited from the bottom of the plane, just like every negative quadratic we've ever graphed. These traits will be true for every even degree polynomial. If you can remember the behavior for quadratics, that is, for parabolas, then you'll know the end behavior for every even degree polynomial. Now let's look at some polynomials with odd degree, cubics in the first row, and polynomials with a degree of 5 in the second. As you can see above, odd degree polynomials move in opposite directions. If they start down, that is, entering the graphing box through the bottom, and go up, that is, leaving the graphing box through the top, they're positive polynomials. But if they start up and go down, they're negative polynomials. This behavior is true for all odd degree polynomials. If you can remember the end behavior for cubics, or technically for straight lines with positive or negative slopes, then you will know what the ends of any odd degree polynomial will do. All even degree polynomials behave on their ends like quadratics. All odd degree polynomials behave on their ends like cubics. Let's try one more practice problem. Which of the following could be the graph of a polynomial whose leading term is negative 3x to the power of 4? To answer this question, the important things for us to consider are the sign and the degree of the leading term. The exponent says that this is of degree 4 polynomial. 4 is even, so the graph will behave roughly like a quadratic. Namely, its graph will either be up on both ends or else be down on both ends. Since the sign of the leading coefficient is negative, the graph will be down on both sides. The actual value of the negative coefficient is negative 3 in this case. It's actually irrelevant for this problem. All I need to know is the minus part of the leading coefficient. Clearly, graphs A and C represent odd degree polynomials, since their two ends head off in opposite directions. Graph D shows both ends passing through the top of the graphing box, just like a positive quadratic would. The only graph with both ends down is graph B. Right, now that we've had some practice together, it's your turn to try out some problems. Pause the video as you try your hand. Thank you for tuning in. Hopefully you were able to follow along and understand the behavior and forms of various functions. Check out the links in the description below for further resources to help you master this topic. All of these resources can be used to help you complete the short quiz associated with this week's lesson. If you have any questions or concerns, feel free to reach out via comments in our Google Classroom or via email. We're always here to help.